Now, particle size distribution, we just go back over here. By default, it says that the mesh type is user, which has 10 interval, 0 to 20, 20 to 40, 40 to 60. So basically, this is the mesh size that it has defined for you. Okay, but there is no binding on you to go with this kind of mesh size. By default, it is saying that your size unit is in micron. It is from 0 to 200. So what is the guarantee that your feed stream will always have the solid component within this particle size? There is no such guarantee. Your particle size may be in millimeters or in centimeters. For a coarse particle, it may be in centimeter size. Okay. In the jaw crusher, you have chunks. It may be 10 or 15 millimeter size. So micron is not an ideal size unit that will suffice for you. And also the range. I mean, 0 to 200. How do I know that 0 to 200 is the ideal size for us? And that also, this 0 to 20, 20 to 40, that mesh size is ideal for us. Okay, so you can change this mesh size as per your requirement. So Aspen Plus gives you that liberty. So if you say that I have say 5 intervals, so you choose 5, immediately it will reduce from 1 to 5, and then you can say my first size is say 0 to 10. Okay, the moment you place 10 over here, then the lower will be fixed at 10. Okay, the moment you push 10 over here, 10 will come automatically over here, because your upper limit over here has been set as 10. So the lower limit for the next mesh size will be automatically fixed at 10. And it will wait for your next entry. So the next entry, you can say, my next entry is say 50. As soon as you put 50, the third entry, lower value, it will change from 40 to 50. Okay. Then you are saying it is 60. You can make it 65. And then the next one you can make 70. And then it may be 90. So these are the mesh types that you can define as user defined. Or you can say my mesh type will be equidistant with 5 intervals between 0 to say 100. Okay, so from 0 to 100, 5 intervals. So, and the size unit will be millimeter. So what will be the intervals? 5 intervals, 0 to 20, 20 to 40, 40 to 60, 60 to 80, and 80 to 100. So these are the equidistant mesh type that will be created for you. Okay, so you can just change the number of intervals. If you say my number of intervals will be 10, in that case, so if you create a new PhD mesh, you will have 0 to 10, 10 to 20, 20 to 30, up to 90 to 100. Okay, so that's how you create equidistant mesh size. The next one is geometric. What does it mean? It means each interval covers a factor of 2 in particle volume. The upper limit is obeyed upper limit is obeyed strictly, the smallest class will contain the specified lower limit. What does it mean? It means the upper limit and the lower limit, their volumes, the ratio of the volumes will be 2. That means if the upper limit is, say, du, the diameter, and the lower limit is dl, then 4 by 3 pi r cube by 4 by 3 pi, the ratio of the two will be 2. So that necessarily means this cancels and other things will cancel. So du by dl cube will be 2, or du by dl will be cubic root of 2. Okay, so let us check this. What is cubic root of 2? We have Excel file. So sorry, Excel file. Let us say what is cubic root of 2. It is 2 to the power 1 by 3. So it is 1.25992105. So the ratio between du and dl will be this. Let us see whether it follows that way. Let us say we want geometric. It will override. I will come to this discretization later. It is a number between 1 to 4. Let us say 1, and the upper and lower limit, say 2 to 20. Okay, so we are creating a mesh between 2 to 20 in such a manner that in each mesh size, the ratio of the diameter of the upper limit and lower limit will be cubic root of 2. Okay, so create. So that is created. Okay, so each and every upper limit, the ratio between each and every upper limit and its corresponding lower limit is supposed to be cubic root of 2. Let us take an example. Say, let us take this example, 6.29961 by 5. What is that? 6.29961. So take this once again. 6.29961 by 5. It is 1.25992. So the ratio is cube root of 2. Okay. Let us take another one. Say this one. This one is very simple. You can see 12.599 by 2 by 10. It is 1.592. Take this one. 3.1498 by 2.5. 3.1498. So 3.1498 by 2.5. $1.2599. Okay, so each and every upper limit by the corresponding lower limit, the ratio is cubic root of 2. Now, what is this discretization 2, geometric discretization 2? If you increase it like this, then here also you can create a mesh size such that the ratio, the du by dl, that will be square root of 1.592. So it will be square root of this. Okay, check. So what is the square root of this? SQRT of this one. It is 1.12246205. So create a mesh with this geometric discretization. Check this one, 5.61231. 5.61231 by 5. So it becomes 5.61231 by 5. It is 1.2246. So that way, I mean, you can test others also. You will find the same result. Okay. For instance, you have this number. You divide 11.2246 by 10. You will get 1.12. Similarly, if you use the discretization of 3, then it will create the du by dl ratio as something like this. Okay. So it can go, this can go up to 4. In case of 4, it will be like this. Okay. So that's how geometrically you can create the mesh. And the third one is logarithmic. Now, what is logarithmic? Logarithmic is the ratio between the size limits of each interval is constant, chosen to meet the specified number of intervals and upper and lower limits. So basically you have taken 20 intervals, upper limit and 2 to 20 millimeter range. So if you create the mesh size, you will find the ratio between any upper limit and any lower limit will be same. So take an example. Say the first one, this by 2, this will be or you can simply copy it and paste it over here. And this one, paste this over here. And then this is equal to this by this. Check the ratio and do it for all of them, and you find the ratio is same for each upper and lower limit. So this is logarithmic distribution of mesh. So that's how you can create a particle size distribution mesh. Okay. Now, you may not have a single particle size distribution. For instance, you have a potassium chloride powder that has one particle size distribution and coal that has a different particle size distribution. Okay? In such situation, you can create multiple such particle size distribution using this new. So, you can say PSD of coal. Okay? So, you can fix it as, say, 4 in, say, inches. It's creating. So, 0 to 2, 2 to 3, 3 to 5, 5 to 6. Now I have given the name PSD coal, but it's just a name. You should give a name which you can really identify with. Okay. Now let us go back to this input, and here you see the particle size distribution. There are two options, PSD or PSD coal, that you have created. Now, so here you have the liberty to choose your particle size distribution. Now, let us choose PSD. Okay. So if you choose PSD, then the logarithmic PSD that you have created, the logarithmic PSD mesh type that you have created, that is shown over here. And now you have to just put the weight fraction. Okay. So you have the sample. Now you have to say what is the fraction of particles that fall under the particle size between 2 to 2.24404. So you have to identify that. Okay, and that fraction you have to put it over here, and cumulative weight fraction will be calculated by itself. Okay, so these are the entry that you have to give, and this is user specified values. So let us take an example. I have some PSD data that I have taken from some source. Now we have to work with this. Now you see the number of data points that I have is up to 549. So I have 549 samples, and the sample ranges between say it is minimum value is minimum value is 11.54 and the maximum value will be 71.13. So these are the minimum and maximum values of the size. Okay. Now let us create say logarithmic distribution between 11 to 72. Okay, and check. So we go back to our PSD mesh. You can edit it anywhere. So there also you can edit, here also you can edit. So this is logarithmic interval. Say I will reduce the interval to 10. Okay, and it is between 11 and 72. Okay, so I create this mesh. So now the mesh size has been created. So 11 to 13.275, 13.27352 is 16.017, 16.017 to 19.3275, etc., up to 59.7676, 6676 to 72. Okay. Now I have to feed in this weight fraction data. Okay. For that, let us go back to our Excel file, and first let us take these values, copy, and put it over here. Okay. This is the lower limit. This is the upper limit. And we will count if S B2 to B50, B550, comma, greater than equal to and the cell is G3, comma, range, comma, less than and H3. Okay, so it should be count IFS. Yes, so it has counted the entire range and wanted to find out how many of these sizes they fall within this limit, 11 to 13.27. So it finds that out of 549 odd sizes, 235 or 225 they fall under this limit. So if you continue over here, you will find the entire distribution, that in the next distribution of 13.27 to 16.02, you have no size at all. Again, from 16.02 to 19.33, it is over 120 data points. Although the data is skewed, but we have got some particle size information. Now we can find out the weight fraction or the number fraction. So it is, say, this by 549, because 549 is the total number. So this is the fraction. Okay, and if you continue up to this, it is like this. Okay, and you copy, go here, paste, and you see the weight fraction. In this case, is a number fraction, but the idea is same. So the weight fraction has been given over here, and the cumulative weight fraction is calculated over here. So cumulatively, it will go up to 1. Okay. So that is how you can fix your weight fraction over here. So this is how the user specified values can be entered in the PST. Now, if you do not have any user specified value, if you want to key in some PST function, okay, particle size distribution function, that is also possible, then you have to use the distribution function option over here. There they will give you the types. There are several types. This is the GGS. Now what is GGS? GGS is, you can search help. This is Gates-Godin-Schumann distribution, and it is given as the cumulative distribution function is d by d max n for d less than d max, and it is 1 when d is greater than d max. Okay, that's how the GGS distribution function is given. Now in this case, you have two parameters. One is n and another is d max, that you have to specify. So other distribution function is RRSB. Now what is RRSB? RRSB is Rosen-Ramler's Sperling-Bennett distribution function. Okay, and it is also called Weibull distribution. So you have to specify the dispersion parameter n and d63 as described over here. So here we have two things. One is n, that is dispersion parameter, another is d63, particle size diameter of RRSB distribution, where QD is equal to 0.632. So you have to mention this n and d63 over here. So this is the place where you put the value of n, and this is the place where you have to put the value of d63. And the next function is normal function. So normal function is, again, you can see the normal distribution function. This is given by QD is equal to half of 1 plus ERF d minus d50 by sigma d root over t. Okay, what is ERF? ERF is the error function. How to define error function? So error function of x is equal to 2 root over pi 0 to x e to the power minus t square dt. So that we call as error function. And finally, you have log normal distribution function. For that, you go to the log normal thing. Here you will find, here also you have this error function, and here you have to use this DLN, which denotes the geometric mean deviation of the variable, and here also you find D50. Okay, now these two things you have to mention over here, geometric mean difference and D50. Now all these things you find D50, D63, what are they actually? So it gives us some kind of curiosity. What are these D50s and D63s? So that also we can learn from here. So just press D50 and it will be clear to you what they are. You just go over here. So these are the properties related to solid particles. So what is D10? It is the number mean diameter defined by this. Okay, and its calculation is something like this for all the particles. So sigma is for all the particles. This is diameter of average surface area. So when you calculate, the expression will be something like this. So it is also a measurement of length. Then it is length mean diameter. This is D30, diameter of average volume, and so on. And then comes few more definitions of D10, D20, D25, D50, D63. So these are the two things that we have come across in the distribution function. So what is D50? It is particle diameter which is larger than 50% of the solid mass. Okay? So it is defined as that. And what is 63? It is particle diameter which is larger than 63.2% of the particle mass. They are defined in this manner up to D100. D100 is the maximum particle size because this is the diameter which is larger than 99.9% of the solid mass. So practically it is the largest particle size diameter. Okay. So here you will find some more definitions. What is Q0D50? It is particle diameter which is larger than 50% of particle number. Okay. Previously D50 is particle mass, and here it is number, not mass. Okay. So that's how we define various notations. Okay. And these notations will come in various solid handling equipment that you use. Okay. So we have so many distribution functions, GGS, RRSB, normal and log normal distribution functions are available for use. For instance, we use the normal distribution function. In that case, we have to specify the standard deviation and D50 value. That is the particle size which is more than the 50% solid mass. Now, both of them will be in millimeter. So we choose millimeter over here for both of them. And if it is from 11 to 72, let us choose the D50 at somewhere in the middle. So it might be somewhere at 30 or 35. Let us say 30. 30 is the D50 and the standard deviation. So let us take 10 and then we can calculate the standard deviation. So this particular particle size distribution curve is produced where particle size is from 0 to 72. Actually, it is from 11 to 72. And the cumulative mass fraction is from 0 to 1. It has been shown like this. Now, if you want to decrease the standard deviation a bit, then this curve will be a bit steep. In such situation, if you say choose instead of 10 millimeter, if you choose say 5 millimeter standard deviation, then obviously the curve will be a little bit steeper. Okay. So that's how you can create a particle size distribution using the function. But whatever you use, whether you use your own data defined by your own specified value, or you use distribution function, you will definitely have a cumulative weight fraction of your particle size distribution, and that can be used for your subsequent simulation calculation. Okay, now we have created the particle size distribution, but still we find this one to be half red and half white. It necessarily means that the information input of the feed stream, or the stream that we are defining, S1, this is not yet complete. Now, what may be wrong? We have given all the information, but still it is showing incomplete. The reason behind this is the temperature and pressure mentioned over here are 30 and 2 centigrade and bar respectively, whereas in the mixed substream it is 25 and 1 bar. Okay, so that means in a single stream we are choosing two substreams which are having different temperature and pressure, and as per Aspen norm it is not allowed. Okay, your each and every substream should have same temperature and pressure. So we have to choose 25 degrees centigrade and 1 bar pressure, and then only it will be blue ticked. Okay, either you change it to 25 and 1, or you change the mixed stream to 30 and 2 bar, 30 degrees centigrade and 2 bar. So this knowledge is very important. Please remember that temperature and pressure of all the substreams should be same in order for the input specification to be complete. Okay. In the similar manner, you can give the information of non-conventional components. Here we have chosen coal, so you can give the information of coal flow rate, temperature and pressure. Then you are ready to do the simulation with that stream. Okay. So with that, we come to the end of this lecture. Thank you.